Hello students, and welcome to lesson 18, our lesson on simplifying radical expressions. When you go into college algebra, which is MAT 150, comes after MAT 114, this is going to be an exceptionally important skill to have because we work a lot with radical expressions in that class, and especially when you're using the quadratic formula to solve for roots of quadratics, you're going to need to know how to simplify a radical expression. Okay, so the skills in this lesson, absolutely important moving forward. What we're going to do is learn how to simplify radical expressions, then we will add and subtract radical expressions, and finally we will rationalize denominators. Okay, the application we're building up to is trying to simplify the expression we see here, which is in the format of the quadratic formula, which is a formula that you use to solve for the roots of quadratic expressions or quadratic equations. So we will come back to that one at the end once we have a little bit more knowledge about how to simplify radicals. But let's just go ahead and get into it. So simplifying roots. If we want to write a root such as 144 p to the fifth in the form a radical b, our goal is to bring groups to the front of the radical where the size of the groups is determined by the index of the radical. Okay, if you don't remember what index means, refer back to lesson 17 where we talk about all the ins and outs of what a radical is. All right, but the index is going to be the number on the radical. So when we don't write the number, it's a 2. So in problems 1 and 2 here, there is no index written, which means it's automatically a 2. But if there's another number there, that is going to determine the size of the groups that we need to pull out. Okay, so now what is he talking about groups? So our goal is to make square root 144 p to the fifth look as simple as possible. And simple is going to mean this form a square root b, where we can't pull anything else out of the inside. All right, so now let's see how to pull things out. Well, we saw previously that square root of 100, for example, is equal to 10, where it didn't feel like it when we did it, but we were pulling out a 10 from the radical. Because on the inside of that radical, square root 100 was actually 10 times 10, and the index of the radical was 2, so I was allowed to pull two 10s on the inside to the outside to have them become 110 on the outside. So what happened there is the index being 2 told me that two 10s become 110 when I pull them out. Okay, group of two 10s, when I pull it out, becomes 110 on the outside. And I didn't leave anything else inside this thing, so I just have that 10 left over. For this lesson, though, we're going to have something left over most of the time. All right, so without more further ado, let's get into example 1 here. What you want to do to simplify radicals is write radicals in their prime factorization. That way you can establish what groups are inside of there. So what I'm going to do is take the number 144 and write it as its prime factors. So I'm going to create a little factor tree to figure out what divides 144. Okay. In this case, I know 144. And by the way, if you know a simpler answer to get to there quicker, don't worry. I'm going to break it down into the most steps possible, basically. But you can always skip steps once you get the hang of it. So when you don't know what divides 144, you just start dividing by things you know work. So since it's an even number, I know it's divisible by 2. When I divide 144 by 2, I get 72. So I write 2 on one side, 72 on the other. Break down 72, and I get 36 times 2. Break down 36, and I get 18 times 2. Break down 18, I get 9 times 2, and 9 is 3 times 3. Okay, so now why did I do all that? Well, I'm looking for groups of 2. So my index on my radical was a 2. So the fact that I have a 2 up here means I want to find groups of 2. So I'm going to highlight things in pairs. I have a 2 here and a 2 here, that's one group. A 2 here and a 2 here, that's another group. And a 3 here and a 3 here, that's a third group. So I have 3 different groups of numbers that I can pull out to the front of this radical. So I can rewrite 144 p to the fifth as I'm going to pull out from each of these highlighting I just did, 2 numbers become 1 number. Okay, so the 2 yellow 2's become 1 2 on the outside. The 2 pink 2's become 1 2 on the outside. And the 2 pink 3's become 1 3 on the outside. So now I have 2 times 2 times 3, where it's the yellow 2, a pink 2, and the red 3. Okay, again, pairs of 2 become 1 on the outside, and I have 5 p's now on the inside. But you might be thinking, hey, why are we leaving it as p to the 5th? Well, let's break it down even farther, okay? On the outside of this thing, 2 times 2 times 3 is 12, and p to the 5th on the inside, sorry about the keyboard, is the square root of p times p times p times p times p, where I can now look and say there's 2 p's here and 2 p's here, so I have 2 groups of 2 p's, which means I can pull out 1 from each of these. So this is going to become 12 times p, where I leave behind the square root of p. Okay, so what just happened there? These 2 p's come out to be this p, these 2 p's come out to be the second p, and the odd p out stays inside the radical. So I'm looking for groups of 2. So I have a group of 2 and a group of 2. Each group becomes 1 p on the outside. So now when I write this together, this is 12 p squared square root p, where I just put those p's together. Okay, so now we could have done this a lot faster. Okay, well, now that we've seen the kind of long way of doing it, we know that the square root of 144 is 12. So instead of breaking it down into all these factors, I could have just gone straight to 144, the square root of it is 12. And for p to the 5th, all you do is divide the exponent by the index, so 5 divided by 2 in this case. And whatever the quotient is, 5 divided by 2 is 2 with a remainder of 1. So the quotient is 2, that's how many p's I take out, and the remainder is how many p's I leave behind. So let's try the second one and see if we can do it a little quicker. The first thing I'm going to do is rewrite the number broken down into its prime factors. So 27 is 3 times 3 times 3. All right, it's 3 3's written together. But I don't really have to write it that way, okay? I can write it as 3 to the power 3, which is also 27. So whichever way you prefer here is totally fine. But we're going to leave the 6 x's together and the 9 y's together. So now what I'm going to do is I'm going to look for groups of 2 on the inside. So there's 2 3's here. Those are going to come out and become 1 3 on the outside. From these 6 x's, okay, if I divide 6 by 2, so on the side here, do 6 divided by 2, I get 3. So 6 x's on the inside become x cubed on the outside. And 9 y's on the inside, if I do 9 divided by 2 up here, I get 4 with a remainder of 1. So I take 4 y's, y to the power 4 to the outside, but I'm going to leave 1 y on the inside. So what I have left behind is 3y, where the 3 was from up here. Okay, we had 1 3 that went unused, and I'm going to have 1 y that gets unused because of this remainder. When I divided 9 by 2, I got 1 y left over, and that stays on the inside. All right, so all in all, I have 3x cubed y to the 4 square root 3y. Okay, now adding and subtracting, the only real thing you have to do here is make sure that the radicands and the index are the same, and then you can add and subtract these as if they were x's. So let me remind you that 2x plus 3x equals 5x, where as long as x and x are the same, we can add together the coefficients 2 and 3 to get 5. Same idea here. So for number 3, 9 square root x plus 5 square root x just equals 14 square root x, where because it's root x and root x, they're both square roots, so the index is 2 in both cases, and the inside, the radicand, is x in both cases, we can just go ahead and add together those coefficients, 9 and 5, to get 14 square root x. For number 4 and 5, it's a little more work though, because we don't have the same radicand on the inside. So we have root 2 on the left plus root 18 on the right here. What we want to do is break down root 18 the way we did in the previous slide. What it's going to end up looking like is 3 root 2. But the question is, why 3 root 2? Well, let's break down root 18 to be 3 times 3 times 2. Okay, so that's the prime factorization of 18. Now that I've done that, 2 3's on the inside become 1 3 on the outside, and I leave the root 2 behind. Okay, and we had a square root 2 in front this whole time. So now I have square root 2 plus 3 square root 2. Together this becomes 4 square root 2. So once I get it to where the radicand and the index are the same, then I can go ahead and just add together the 3 plus the 1 that's in front over here to get a 4 as my new coefficient. Okay, number 5, we're going to have to do a little bit more work even. I have negative 3 square root 27x, and I have 10 square root 48x. Those do not look the same at all. Okay, the indexes are the same, but the radicands are completely different. So the first thing we're going to do is break down the insides. So we have negative 3 square root 27 is 3 times 3 times 3, and I still have an x. Then 10 square root 48 is 10 square root 48 is 12 times 4, but that's not quite broken down enough. So let's break it down. 12 times 4, 12 is 3 times 4, 4 is 2 times 2, and this 4 is also 2 times 2. So notice up there I have 4 2's and 1 3. So 2 times 2 times 2 times 2 times 3, and I still have an x. All right, so now let's look for groups. Okay, I have a group pair of 3's right here where I need 2 3's to become 1 3 on the outside. I have one set of 2's that'll become a 2 on the outside, and another set of 2's that'll become 2 on the outside. The negative 3 is still in front of this first radical, and I multiply it by the new 3 that comes out, and I have square root 3x left behind because this 3 and this x stayed on the inside. Then I have plus 10 times 2 times 2, and another square root 3x left behind because again this 3x did not get used, they had no pairs. So now if I simplify what's in front, negative 3 times 3 is negative 9 square root 3x, plus 10 times 2 times 2 is 40 square root 3x. And now I just add together the coefficients. Negative 9 plus 40 is positive 31, and that square root 3x stays there. But before I could add together anything, I had to make sure that the radicand was 3x in both groups. All right, let's move on. Rationalizing denominators now. To rationalize a denominator means to rewrite the rational expression without having a radical in the denominator. To do this, we multiply the numerator and denominator by the conjugate of the denominator, where conjugate means to change the sign in a binomial. So a plus square root b is the conjugate of a minus square root b, and vice versa, where all we do is change that plus to a minus. Okay, if you remember from multiplying polynomials, we learned difference of squares, okay, where difference of squares is multiples, products of conjugates. So if we multiply something times its conjugate, we get a difference of squares. Okay, difference of squares here, where a plus square root b times a minus square root b, all we do is we square the first thing and square the second thing. So for example, square root a plus square root b times square root a minus square root b, you square square root a to get a, you square square root b to get just b, and then we left with a minus b. All right, if we have a simple denominator where it's just 3 square root 5, for example, so there's no addition or subtraction, then all we have to do is multiply by the square root of whatever b is. So we're going to see that number 6 is going to be easier, number 7 is going to be a little harder. All right, so for number 6, we want to get the radical out of the denominator. Right now we have 1 over 3 square root 5, so we're going to multiply top and bottom of this thing by square root of 5, where I'm multiplying by whatever this radical is. We have to do it on top and bottom because notice root 5 over root 5 just equals 1 because it's the same thing on top and bottom. So they cancel out to just be 1, which means we're allowed to do this. We're going to change the way it looks, but we're not going to change the value. Okay? When we multiply this out, on top, 1 times square root 5 is just square root 5. And on bottom, 3 square root 5 times square root 5 is 3 times 5, because square root 5 times itself is just 5. Okay, that's a property of square roots. When you multiply a square root by itself, you just get whatever the radicand was. And so right now we have root 5 over 15, and there's no way to simplify that because root 5, nothing can be pulled out. So we're done. 1 over 3 square root 5 is equivalent to root 5 square root 5 over 15. All right, number 7 is a little bit more work. We have 4 plus square root 2 over square root 2 minus square root 3. We have to multiply top and bottom by the conjugate of the denominator, which is root 2 plus root 3. Okay, we change the minus to be a plus, and we multiply that by that on top and bottom. In the numerator, we have to actually distribute out all these terms. So I'm going to multiply 4 times square root 2 and square root 3, and then multiply square root 2 times square root 2 and square root 3. When I do that, 4 times square root 2 is 4 square root 2. 4 times square root 3 is 4 square root 3. Square root 2 times square root 2 is just 2. And square root 2 times square root 3, when you multiply radicals, you multiply their radicands. So this is square root 6. Okay, in the denominator, we have the difference of squares here because we are multiplying conjugates. So square root 2 times square root 2 is just 2, and square root 3 times square root 3 is just 3, and you subtract them from each other. When we simplify this, the denominator is just -1, and the numerator actually doesn't simplify at all. So I'm going to write it exactly the same. 4 square root 2 is 4 square root 3 plus 2 plus square root 6. I know, real ugly, but that's okay. And because we have a negative in the denominator, we can move that negative to the top, and all of our terms on the top are going to become negatives of what they were before. But now we don't have to write a denominator anymore. So we just get this long expression. It's negative 4 square root 2 minus 4 square root 3 minus 2 minus square root 6. And that may not seem simplified, but the goal was to rationalize the denominator, not necessarily make it look nicer. All right. So we're all done rationalizing the denominator. One more step for this lesson. We got to simplify this expression at the top. So we have 8 minus the square root of 8 squared minus 4 times 1 times 5 over 2 times 1. First thing we're going to do is multiply out the inside of this thing. So we have 8 squared is 64, and 4 times 1 times 5 is 20. And on the denominator, 2 times 1 is 2. If I simplify the inside more, we have 8 minus square root 44 over 2. Okay. Now, square root 44, we want to break down. Okay, so on the side over here, 44 is equal to 11 times 4, and 4 is 2 times 2. So I can pull out one of those 2's to the outside and leave the 11 behind. So square root of 44 is going to be 2 square root 11, and this is all over 2 still, where this pair of 2's became this 1, 2 on the outside, and the 11 stayed behind on the inside. Then, because everything on top is divisible by 2, I can simplify this by doing 4 minus root 11, where I did 8 over 2 and 2 over 2. And that gave me 4 minus 1 times root 11, but we can just leave off the 1, and we have 4 minus square root 11 as our answer. All right, that was how to simplify radical expressions. We'll have plenty of practice in class. Hopefully you guys are looking forward to it, and we're going to get really good over this at the coming days. Really good at this over the coming days. Gosh, English is not my strong suit. It's a good thing I teach math instead. All right, see you guys next time.